Hello calculus student, and welcome to our exciting video on the mean value theorem. So the mean value theorem is a theorem that relates the average rate of change of a function to the instantaneous rate of change at some point on the interval in which you're considering the average rate of change. Here's a picture kind of illustrating that. So we've taken 2 points, x equals a, x equals b here, and we've computed the average rate of change of f of x with respect to x on the interval from a to b. That's given by this quotient here. As we've seen before, this average rate of change is also equal to the slope of the secant line determined by the points a, f of a, and b, f of b. So we've kind of illustrated that all here. Let's imagine sliding the secant line until it's tangent to the graph. So if we illustrate that, we're going to take this secant line and just slide it down this way, keeping it parallel, and we can see that if we slide it to about this position, it'll turn out to be tangent to the graph. And this is a graphical illustration of what the mean value theorem tells us. So if we slide the secant line, we see that there is some point C, that's right it, where the tangent line ends up. And the C is between A and B. That's going to be an important part of the conclusion of the theorem. And the line tangent to the graph at CF of C is parallel to the secant line determined by AF of A and BF of B. So here's an illustration of what we're looking for, how to talk about this point where the tangent line is parallel to this secant line. And we want, again, this to happen somewhere on the interval in which we're considering the average rate of change. So here's a statement of the mean value theorem. We assume we have a continuous function f defined on some closed interval. Remember, closed means the endpoints are included. So a less or equal to x less or equal to b. And we want this function to be differentiable, so it has a derivative at every point in the open interval, a less than x less than b. If all this happens, then there is always a value of c somewhere between a and b, so that the difference quotient, fa minus fb over b minus a, this is also average rate of change, or slope of the secant, but this will end up equaling f prime of c. So you can either think of this as an average rate of change equaling an instantaneous rate of change, or a slope of a secant equaling the slope of a tangent. So we've just repeated the picture of the previous page. Here's what that looks like in a geometric setting, the secant line in red and the tangent line in green. So the mean value theorem tells us only that there is some value x equals c satisfying the above equation. That is f prime of c equals f of b minus f of a over b minus a. There actually may be more than one such c. We're always going to require this c to be between a and b. As we'll see, it can be very difficult or impossible to actually find the value of c, but in many applications of the mean value theorem, this is not important. In fact, most important sometimes is just to know that such a c exists, but actually knowing what it is may be secondary. We'll do one exercise where we find the value of c, but in most cases where the mean value theorem is applied, we'll just know that there is a c between a and b that has this property, but we won't care or often won't be able to find out what that c is. So as our example of actually finding the c, let's take the function g of t equals t cubed minus 12t minus 3. We'll find a number c between 1 and 5, so that g prime of c is g of 5 minus g of 1 over 5 minus 1. So let's check that the mean value theorem holds first. So first note that g of t is continuous on this closed interval, 1 to 5 endpoints included, and it's differentiable on this open interval from 1 to 5. Now g of t is just a polynomial, so of course it's continuous and differentiable everywhere. But because these two conditions hold, we can draw the conclusion by the mean value theorem that there is some value of c between 1 and 5 satisfying equation 1. Find that C really is a pretty easy algebra problem in this case. I'll let you check that if you plug in 5 for t, you find g of 5 equals 62, and g of 1 equals minus 14. And the derivative is very easy. G prime of t is 3t squared minus 12. So the C we are seeking is the place where g prime of c, there it is equal to the average rate of change from 1 to 5. So g of 5 minus g of 1. That's 62 minus 14 over 5 minus 1 gives us 19. So our goal is to find the C for which this equation works, and of course we require that C be between 1 and 5. This is a very easy algebra problem, so we have the equation 3c squared minus 12 equals 19. Bring the 12 to the right, divide by 3, take square roots, and we find there's two values of c that might apply. C equals plus or minus the square root of root 31 over 3. Now we're looking again for c in the interval from 1 to 5, so the negative square root doesn't count, it falls outside that interval, so the only answer we keep is this one. So the minus root 31 over 3 is not in the interval 1 to 5, so not the answer we were looking for in this case, so we just discard that solution. Here's a picture of the situation. So we've drawn the cubic g of t here and filled in the secant line, which has slope of 19, as we saw up here. Okay. And we now are going to take a look at what happens at this point, root 31 over 3. By the way, here's the point minus root 31 over 3, again, outside the interval from 1 to 5 that we're working with over here. So now in orange, we've drawn in the line tangent to the graph, y equals g of t at the point where t equals root 31. And notice that tangent line does appear to be parallel to the secant line, so they both have slope 19. In fact, it's easy to check if you plug root 31 over 3 into the derivative, g prime, you come up with 19. And of course, g prime is the slope of the tangent line at a given point. Maybe wonder about this other point. Well, it turns out that the tangent line at the point c equals minus 31 is also tangent to the secant line. It was just outside the interval, so we didn't count it. But here is that other line that would arise had we taken into account the minus root 31 over 3 root. So all three of these lines are parallel, and it's at this point that the mean value theorem guarantees, the one between 1 and 5. Now, every time you apply a theorem in mathematics, you've got to make sure that the conditions that are supposed to be true in the theorem apply. And it turns out if you try to apply the mean value theorem to a function that is not continuous on the closed interval or not differentiable, then the conclusion of the mean value theorem may not hold. So we always want to check the conditions are met. We'll see in an example right now that even if one of these conditions fails at just one point, that's enough to throw off the whole mean value theorem. So as our example, let's take capital G of x equals absolute value of x. And note that g of x is continuous on the closed interval from minus 7 to 5. In fact, the absolute value function is continuous everywhere. But we're going to show that there exists no c value between minus 7 and 5 for which the mean value inequality holds. So in this equation, g prime at c equals g of 5 minus g of minus 7 over 5 minus 7 has no solution. And of course, we haven't talked about the differentiability. We all know that the mean value theorem is not differentiable at the point x equals 0. The graph has a corner there. So doing our calculations, we first compute g of 5 minus g of minus 7. And we get our result. Here's s value of 5. And Here is the absolute value of minus 7, so 5 minus 7 is minus 2. Over 5 minus minus 7 is the 12, and hence we get a result of minus 1/6. And for the absolute value function, well, we know what the graph of that looks like. We have a ray of slope minus 1 coming into the origin there, and then a ray of slope 1 coming out. Bad drawing. And of course, we have a corner here at the origin where the derivative does not exist. So the derivative of g prime, we can write it very easily in piecewise form. Minus 1 when x is less than 0. There's the line of slope minus 1 that constitutes the graph. 1 when x is greater than 0, line of slope 1 over there, and it does not exist at the origin. And that's enough to tell us there's no value c between minus 7 and 5, with g prime of c equals minus 1/6. And in fact, just looking at the possible values for g prime, there's only 2 of them, minus 1 and 1. You're never going to get 1/6. So in this case, we'd say the mean value theorem does not apply because, and if we go back and check the hypotheses, we found that we did not have differentiability on our open interval minus 7 to 5. Here's a picture of the situation, the graph of the absolute value function, the 2 points with x coordinates minus 7 and 5, and the secant line of slope minus 1/6. And again, this non-differentiability here kills us. If you try sliding this tangent line sideways, you can hit this point here, which is certainly parallel, but that is not a tangent at that point because the absolute value function has no tangent at the origin. Now, as mentioned earlier, finding or not finding a value of c is actually a very unimportant application of the mean value theorem. The theorem can also be used to learn important things about the behavior of functions. So we're going to give one easy example of that. And this example says, use the mean value theorem to show that for every real number a and b, if we take the sine of a minus the sine of b and take the difference, we can never be bigger than the absolute value of b minus a. This is a very quick application of the mean value theorem. So again, let's check that the theorem applies. We will assume that a is less than b. So we have a left and a right endpoint for our interval that we know about. And of course, the sine function is one of the better behaved functions we work with. It is continuous on the whole real line, so certainly on any interval from a to b. And it's also differentiable everywhere. The derivative is the cosine, so it's also differentiable on the open interval from a to b. And by the mean value theorem, because these two continuity and differentiability conditions hold, we know that there is some number c between a and b, so that the sine of b minus the sine of a over b minus a is equal to the derivative of the sine function at c, that is cosine of c. Now, trying to find that c, I guess it's possible using inverse cosines, but wouldn't give us much insight. Again, we often don't care what that c is, but here knowing it exists is very important because we're going to take absolute values of both sides of the equation we came up with and use the fact that the cosine in absolute value is never bigger than 1. So taking absolute values, we have the absolute value of sine of b minus sine of a over b minus a is the absolute value of the cosine of c for some c, and that, of course, is no bigger than 1. And finally, multiplying through by b minus a gives us that the sine of a minus the sine of b in absolute value is no bigger than the absolute value of b minus a. And there's the desired inequality. And one very special case that's worth keeping in mind sometimes is this. If we take the special case where b is some number h and a is 0, so that the sine of 0 is 0, then this inequality reduces to saying that the sine of an angle h is never any bigger than h. And of course, we saw earlier that if we take the limit as h goes to 0 of sine h over h, this turns out to be 1. and evidently this thing is approaching 1 from the negative side because the numerator is evidently never bigger than the denominator. So this fraction is always less than 1. So lastly, I just want to mention your textbook opens with a very special case of the mean value theorem that's called Rolle's theorem. The conditions for Rolle's theorem are the same as those for the mean value theorem, but with one small extra condition added. Very simple condition. Here's the statement of Rolle's theorem. Fx is to be continuous on a closed interval again, a to b, and once again we want it to be differentiable on the open interval a to b. And then the extra condition is we require that the function f take on the same value at these two endpoints, f of a equals f of b. And the theorem says then there is a real number c, a less than c less than b, with f prime of c equals 0. In fact, just like with the mean value theorem, in some cases there may be more than one c satisfying these conditions, but all Rolle's theorems tells us is that there is at least one. So you look back at the mean value theorem, which says f of b minus f of a over b minus a equals f prime at c for some c. And of course, this condition f of b equals f of a means that this quotient actually is 0, and so we're finding a place where the derivative is 0. So here's an illustration of Rolle's theorem. In this picture, we have drawn a function f, and we've taken 2 points b and a, and you can see the secant line joining b f of b and a f of a is horizontal. So f of b and f of a are equal for this function. And then Rolle's theorem says that there are some points where the derivative is equal to 0, some points between b and a where the derivative is equal to 0. Here we've drawn in tangent lines at those points. We can see very easily from the graph that there are 2 points between b and a where the function takes the value, where the derivative takes the value 0. That's at this point labeled c1 and c2. So f prime at c1 and f prime at c2 are 0. And again, this is really the mean value theorem in a very special case, where the difference quotient, as we see here, turns out to be 0. The significance of this role is that the c values, of course, are critical values for f. Remember, in section 4.1, we defined critical values. Among other things, they are points where the derivative is equal to 0. And they can often, of course, critical points are important because they often correspond to a minimum or maximum of a function. Okay, so about 3 things to remember in this video. We'll just go over them very quickly. So the mean value theorem can be interpreted in 2 ways. In one interpretation, it relates the average rate of change on an interval to the instantaneous rate of change. This is kind of a symbolic interpretation. It also relates the slope of a secant line to the slope of a tangent line. That's a geometric interpretation. Both these interpretations can be useful, and as we've kind of said in other parts of this course, sliding between the symbolic and the geometric can be very important and really help you in your thinking and interpretation of details. Both the mean value theorem and Rolle's theorem apply only if the function you're working with satisfies these conditions of continuity on the closed interval and differentiability on the corresponding open interval. We saw in the second example that if either of these conditions fails, even at just one point, then the conclusion of the theorem may not hold. When you apply theorems in mathematics, engineering, science, always check carefully that the necessary conditions are true before drawing a conclusion based on that mathematical theorem. Finally, the mean value theorem and Rolle's theorem are both examples of what we call existence theorems in mathematics. Such results often tell you that something exists, in this case just that number c somewhere between a and b, but the theorem may not tell you how to find these objects or anything more about them other than that they exist. But often in working with the mean value theorem and Rolle's theorem, just knowing that the value C exists is enough. So please make sure you review these concepts in this textbook, rewatch the video if you like, and try some of the homework problems on the mean value theorem and Rolle's theorem. See you in the next video. Bye.